So I'm going to give you some insight into wavelets and signal processing. So at this point you might be wondering, what is a wavelet? That is not a helpful question to ask at this point. The more pertinent question is, why wavelets? In more depth, when or under what scenario would one even want to try to use wavelets? We need the underlying motivation behind them first. Most people probably go their whole lives never even hearing the word wavelet, and they still live fulfilling lives. Heck, I might even say nobody really even knows what wavelets are in the first place anyway, because one can invent, construct, or define them however one wants to according to basic initial parameters. But it is wavelets' useful properties that make them interesting and worthwhile to examine. That is why it is better to ask why wavelets to understand the underlying motivation. In order to get to this, we need to tell the story from the beginning. I like to produce original electronic music in my free time, so many of the files on my computer are sound files. Now, what is a sound file? It ultimately is just a big long list of numbers, which contains the information of the shape of the waveform. Most .wave or AIFF sound files store 44,100 samples or numbers for each second of sound. 44,100 hertz is well over twice the highest frequency the human ear can hear, which is 20,000 hertz, which is enough time resolution to overcome the Nyquist-Shannon sampling theorem's sampling rate aliasing frequency. Proof and details of this theorem are covered in any basic signal processing course, which is not a uniquely insightful enough result for this video. So we've got a sound file with 44,100 numbers stored for every second of sound. That's a lot of data to store and or make sense of. So here's an interesting question. What does it mean to quote-unquote make sense of the sound data? Well, of course we could just play the sound on a loudspeaker and listen to it and use our human ear's judgment, or we could plot the sound file to visualize it like shown above. But let's say we wanted to automatically analyze the data to detect certain characteristics, especially with the huge modern craze over automation and artificial intelligence. How would we go about doing this? Well, let's step back for a second. What exactly is our ear detecting? The whole biological, physiological, psychological, and mechanical process of this could be an entire video series of itself, but our ear, at the end of the day, ultimately detects air pressure vibrations of various frequencies. So that's the key word here, frequencies. We want to know what frequencies are present in the signal or sound file. I personally have perfect pitch, so I can immediately tell what note or pitch or frequency something is as soon as I hear it. But even without perfect pitch, most people, even without any prior musical training, can tell if one pitch is relatively higher or lower than another. If one does have some music theory background, one will have some training in listening to and analyzing chords or triads involving multiple notes or frequencies stacked on top of each other, played at once together simultaneously. An A major triad chord has an A as the bottom tonic note, a C sharp as the middle mediant note, and an E as the top dominant note, all stacked on top of each other. An E flat minor triad chord has an E flat on the bottom as the tonic note, a G flat in the middle as a mediant note, and a B flat as the top dominant note, all stacked on top of each other. With some music theory training, the human ear is able to hear, detect, and distinguish all three tones and their frequency relationships in a stacked triad chord even when played together simultaneously at the same time, rather than one after the other in succession. Additionally, we can also detect the relative amplitudes or loudness of the various different frequencies. The human ear can of course detect if the players in an orchestra are too loud compared to the soloist and drown out the soloist when they play together in an ensemble. So these two properties basically illustrate what a linear system is. Even with multiple frequencies simultaneously going off at once, not only can the human ear detect which frequencies are present, but the human ear can also detect the strength of each individual frequency present. And this is one of the most important definitions in the content of most standard signals and systems courses, which for this reason is sometimes instead called linear system analysis at some universities. So of course, by obvious intuition and observation from musical capabilities, the human ear can observe the linearity property of frequencies in any sound wave or sound file. Can this be mathematically done as well? Indeed, yes, but how? We'll talk about this next. This illustrates the depth of the field of signal processing. I'm not going to teach the entirety of the curriculum of a Signals and Systems course in this video, but some of the key basic fundamental big picture concepts are very helpful for the context of the underlying motivation for why wavelets can come in handy in various situations. So the continuous Fourier transform mathematical operation of course takes a continuous function or signal and spits out the frequencies associated with that. But the thing is, computers work in the discrete time domain rather than the continuous time domain. How do we take a continuous Fourier transform, or even just Fourier series on a discrete function, rather than a continuous function? Well, we can't, and that's why typically electrical engineering students take a standard signal processing theory, continuous signals class in undergrad before taking digital signal processing methods course in grad school. Well, interestingly enough, once we're back in the discrete time domain from continuous time domain, now everything can be treated using concepts from linear algebra, such as vectors and matrices, which is more easily understood and accessible without requiring any knowledge of signals and systems. It is worth mentioning that signals and systems is a course taken by specifically pretty much only electrical engineers and is not really a topic pertinent in any other discipline in STEM. The goal is to portray wavelets in a manner that is accessible to as many as possible, yet still without losing or throwing away too many of the important details. Moving forward, I'm going to assume the viewer has an understanding of standard linear algebra, but even if one hasn't even heard the term linear algebra before, I will try to explain and portray the big picture ideas and concepts from linear algebra in layman terms, and if that is not enough, just look at the diagrams and ignore the mathematical details, intricacies, and mumbo-jumbo and focus on the big picture. Remember, this all leads up to why wavelets. So now that we've established computers all work in the discrete domain, remember how our sound file was just a long list of numbers? Well, our sound file, or signal to analyze, literally is just a very big, long, and high-dimensional vector. Let's say our sound file has n samples in total, then our signal vector is n-dimensional and requires n numbers of data to represent the whole total signal. Well, as you know from linear algebra, any particular specific vector can be represented in various ways depending on the basis one wants to express it in. Going west 1 mile, then north 1 mile is the same as going northwest for square root of 2 miles. So let's say we have a sentence in English and we want to transform the sentence or translate it into Mandarin Chinese. That means we're going to express the exact same idea from the English sentence as in the Mandarin Chinese sentence. There's a set procedure for translation between the two languages, and if one knows enough English and Chinese vocabulary plus grammar, one can perform this translation operation. Indeed, we could also translate the exact same original sentence to any language we want and have it still maintain its meaning in whatever language it is translated to, whether it be Japanese, French, German, etc. This idea remains the exact same with vectors. Let's say we have a vector containing information that represents a position or coordinate in standard basis. This is our original sentence in English, and we can easily translate it to any other language or basis we want. So how do we mathematically transform from a vector in standard basis to express it using another basis? Well, from standard linear algebra, the generalized procedure for this involves doing the row-reduced echelon form problem using Gauss-Jordan elimination row operations on the matrix equation above. Assuming our basis is well enough determined, we have n unique basis vectors, enough to be complete for n-dimensional space. This framing of the problem intuitively makes sense. You want to find the coefficients in the new basis that gets you to the exact same location of the original vector or point, or analogously, you just directly find the corresponding words in the foreign language that signify the same meaning. But what if our basis is not well enough determined and our basis is not complete? Let's say we're only given k, which is less than n basis vectors to represent an n-dimensional vector. Yeah, this is a problem. There is no free lunch. If I have the sentence in English, I like math, and no matter what language I use to express this idea, I need to express that me, the subject of the sentence, likes or appreciates the verb of the sentence, mathematics, the direct object of the sentence. If we omit any of those words, the sentence loses some meaning. Now, we might not know who specifically is liking the math, or what it specifically is that I like, or what I am doing to the mathematics, as shown above. In Japanese, for example, it is grammatically acceptable and even common to omit the subject and object of the sentence, but only when the information about those is easily implied or inferred through conversational context. So at the end of the day, unless we find informational compression patterns in the data sequence of n numbers of our n-dimensional vector or sentence, it's going to take at least n basis vectors or numbers to uniquely and completely represent the same idea or information, no matter what language or basis we use. So if we're only given k which is less than n basis vectors to work with, what do we do? If we're only given k which is less than n basis vectors to work with, we want to find the best least squares approximation of our original vector with using only the k allowed basis vectors that were given. Let's say the word or concept of mathematics somehow just did not exist in a particular foreign language, and I wanted to communicate to this foreign language speaker the idea that I like mathematics. I'd have to find the best approximation of this idea in the foreign language so this person could understand to some extent the idea I'm trying to communicate. The standard procedure is to solve the above matrix equation, once again using Gaussian-Jordan elimination to obtain the row-reduced echelon form, RREF. Notice how we basically just took the previous change of basis matrix equation and multiplied both sides by the transpose of the basis matrix. After all, if two things equal each other, doing the same operation to both sides of the equal sign results in another true equation. Now notice how the right-hand side of the equation ends up taking the original vector and projecting it along each basis vector, giving us the projection of the original vector onto the allowed space from the few limited number basis vectors. This basically is like taking the closest fit word in the foreign language to substitute for how an exact fit direct translation does not exist or is not allowed. For example, future events are described ambiguously using the same present tense verb conjugation in Japanese, so to communicate "I will study mathematics" in Japanese, it is common to put a future time marker, such as "I will study mathematics tomorrow," to specifically indicate that the action will take place in the future, something that could possibly be lost in translation as indicated, which is the closest fit to "I will study mathematics" in Japanese, which has no future tense. This is going to get mathematical, but it is interesting enough to note. Let's mathematically compare the jth row of the resultant vector on the left-hand side and also the right-hand side of the equation. On the right-hand side's vector's jth row, we have the original vector projection onto the jth basis vector. On the left-hand side's vector's jth row, we have the sum of the weighting variables for each basis vector times the correspondingly weighted basis vector, then projected onto the jth basis vector. That means in looking at the jth row and restricting ourselves to only looking at the jth basis vector's direction because everything is projected onto that direction, we are solving for or picking the correct weighting variables for each basis vector such that we are balanced on both sides of the equation. In other words, this weighting scheme for the basis gives us the same position as the original vector when restricted to only looking along the allowed jth basis vector direction. We repeat this for every basis vector, and voila, we've balanced the positions for every direction possible in the allowed space, giving our best fit approximation representation in the underdefined space. Notice how we've restricted or confined ourselves to the allowed space spanned by the basis by projecting everything onto the allowed basis. In less mathematical terms, this process is analogously like if we want to translate the sentence "I like mathematics" to some foreign language, but this foreign language doesn't have a direct equivalent translation of the word mathematics. So we start finding synonyms in English for mathematics, like calculus or arithmetic, and related synonyms in the foreign language, and hopefully we find a match between the two that is somewhat close. And there we have it. Using this procedure, we can find the best fit approximation or translation in any basis or language for any vector or sentence. How computationally difficult is this procedure? Well, we have to perform a row-reduced echelon form Gaussian-Jordan elimination procedure. For an n-dimensional system, this requires up to n squared row operations, each row operation of which takes n mads, multiply adds, or multiply accumulates, the standard unit of computation for signal processing. So this has computational complexity of n cubed, which is not good. How do we make this faster? Well, we could intelligently pick a basis or language such that it is orthonormal. In a nutshell, that means there is no overlap between any of the basis vectors, and movement in the direction along any one basis vector creates no movement along any other basis vector's direction. If we intelligently pick a basis or language such that it has this orthonormal property, where the dot product or inner product between any two different basis vectors is 0, this enormously facilitates the least squares computational procedure, or the translation process. For example, it is much easier to translate a sentence from English to French than from English to Chinese, because hey, they at least use more or less the same alphabet, and are somewhat similar. And notice, if we pick a language or basis that is indeed orthonormal, the left-hand side of our least squares approximation equation to solve ends up indeed becoming the identity matrix, already giving us the RREF form of the matrix, eliminating the need to even do any RREF Gaussian-Jordan elimination computations. The only computations necessary are for the right-hand side, where we have to compute n inner products for an n-dimensional system. N inner products of n dimensions is just n squared operations, which can be rewritten as a matrix multiplication above. Look how much we've already improved by. We started with n cubed operations for a poorly chosen language or basis, and we reduced it down to n squared operations for a more intelligently chosen orthonormal language or basis. But can we do better than n squared? Yes, indeed, we can do better than n squared. As previously mentioned, the discrete Fourier transform can essentially be interpreted as a matrix multiplication on a signal vector, which, without any intelligent algorithms involved, will take n squared mads. So how should we go about intelligently designing an algorithm to beat n squared complexity? Well, let's take a closer look at the discrete Fourier transform matrix. Notice how there's a lot of symmetry in it. This makes sense. The complex roots of unity form an algebraic group of symmetries. The discrete Fourier transform matrix is also a unitary matrix transformation, though not Hermitian, and it is also a Vandermonde matrix. Intuitively, by inspection, there should exist some method of more intelligent processing that can beat n-squared complexity. And here's the key equation that demonstrates this. From the definition of the discrete Fourier transform, which is basically just a matrix multiplication, we can intelligently and equivalently rearrange as shown above. And look, we see that the discrete Fourier transform of length n literally contains two smaller discrete Fourier transforms of length n over 2, and of course multiplied by the famous prefactor twiddle factor. Ignoring the twiddle factors for a second, this simplifies our computational cost from n squared to an n squared matrix multiplication to two smaller n over 2 squared matrix multiplications, ends up being n squared over 2, which cuts down our total computational cost in half. That's nice, but can we do that again to save even more computational time? Of course we can. Due to symmetry, a discrete Fourier transform is the same matrix multiplication operation structure no matter what the size. We can continuously and equivalently keep dividing any discrete Fourier transform we have into two smaller discrete Fourier transforms of half the size, which is how the radix 2 fast Fourier transform algorithm is performed as demonstrated by the butterfly diagram. The details of the mechanics of this can be learned in any standard digital signal processing class, but look at the big picture perspective. Here's the question. Unintelligently going about the d of t matrix calculation involves n squared computation. If we keep decimating by 2, what is our final computational cost? Well, let's figure this out. Let's say n is a nice power of 2 for simplicity's sake. In fact, many audio editing softwares like to work in nice powers of 2 for this reason, and 44,100 Hz sampling rate is not a prime number and has a lot of nice factors, so it can use various different radix values to decimate down. That means we can cut n in half log 2n times. We start with n squared computations and break it down in half log 2n times. That means in the end, we'll be left with n single-value discrete Fourier transforms, which literally is just n mads, linear time for the matrix multiplication part, because a discrete Fourier transform of 1 point is literally just a single multiplication. That's really good, but hold up, not so fast. We forgot about the twiddle factors. Each divide in half step requires n twiddle factor mads, and we have log 2n total divide in half steps. That means we have order n log n complexity. The previous extra linear term is not significant in big O notation for intelligently using the radix 2 fast Fourier transform over naively brute forcing the n squared computations for a standard matrix multiplication. And simplifying our computational cost from n squared to n log n saves a lot of time when n is large, which really changes performance quality. It is the difference between being able to analyze and process sounds in real time at a concert versus having to wait for somebody to work with audio post-production in the studio after the concert. Now, before we move on to wavelets, notice the fractal-like and self-similar structure of the fast Fourier transform algorithm, which we will draw parallels to when we talk about the fast wavelet transform algorithm. So the fast Fourier transform is indeed the most useful tool in digital signal processing because it spits out the frequencies present in a signal in somewhat reasonable amount of time. That being said, there are some drawbacks. Order n log n starts to become pretty slow when n gets large compared to linear time processing, order n. That being said again, let's say you have a 3-minute song of n equals 3 minutes times 44,100 samples per second samples. In practice, we generally don't want to go about processing all n samples at once for the entire song altogether. Now, why is that? Let's think about this in terms of layman terms. Most modern pianos have a sustain pedal. When you push down on the sustain pedal, it lifts the damper for the strings, causing all notes or keys pressed to continuously ring even after the finger releases the key, thus somewhat smearing the texture of the piece's performance and, in mathematical terms, the time localization. Used in moderation, this can create beautifully dramatic effects in piano performances, especially effective for compositions by composers in the Impressionist era such as Debussy. However, with too much sustain pedal, the music ends up becoming too smeared or muddy with a cacophonous jumble of ringing notes that don't stop resonating. And that is exactly what happens when we take a Fourier transform over the entire 3-minute song. We end up holding the sustain pedal for the entire song, so to say, and we pick out the amount of each frequency present from the entire song simultaneously, losing all sense of mathematical time localization. That means now we know exactly what notes and which keys were pressed at some point throughout the entire 3-minute piece, but now we have absolutely no clue of when throughout the 3-minute piece each note or key was pressed. and that is a significant negative or drawback for certain applications. So how do we go about fixing this problem? Well, we can look at short successive windows of our 3-minute piece and pick out the frequencies present in each window with an FFT, which sometimes is called the short time Fourier transform, windowed Fourier transform, or Morlet-Gabor wavelet transform. Now we have a nice balanced trade-off of what notes or frequencies were present in the song and at which time, which window those frequencies ended up happening at. This in practice ends up giving the best results and is probably how YouTube can speed up or slow down the playback speed of videos without actually altering the perceived pitch. Think about it. When you play a cassette tape or record player on faster speed, everything sounds higher, and vice versa. You play back on slower speed, everything sounds lower. How do you play back sounds faster or slower without altering the perceived pitch? Well, windowed fast Fourier transform. Note, for this purpose, the window is very small, on the order of a fraction of a second. After all, our ears work that way too. Every fraction of a second, our ears or brain picks out the frequencies present, and our ears don't actually just take a FFT of the entire song, otherwise we'd have no time localization and thus no sense of rhythm. That being said, windowing our signal sacrifices overall orthogonality throughout the entire function, which is not actually a problem for applications like speeding up or slowing down the playback speed without altering perceived pitch. But this can be problematic for applications to other fields like quantum chemistry. So we just mentioned that the windowed Fourier transform gives us a nice trade-off between time localization and frequency localization. Why is there a trade-off? That is because of the time-frequency uncertainty principle, which basically says the variance/second central moment of a signal in time domain times the variance or second central moment of the same signal in frequency domain is lower bounded by a constant. If one variance gets too small, the other variance must get larger to maintain this property and this inequality. Proof of this could be a short video in itself, but it ultimately is grounded in the notion of the generalized function inner product form of the Cauchy-Schwarz inequality, and it is also literally equivalent to the Heisenberg uncertainty principle from quantum mechanics, considering momentum and position wave functions are Fourier transform pairs. So we've established that when we transform our signal into a new language or basis, there are two significant properties we care about. One, the computational cost of the transformation. For the fast Fourier transform, it's n log n. The time localization of the transform. For the FFT on the whole signal, we have no time localization because we have no idea when specifically frequencies happened. The windowed FFT can get around this and is often used in practice. However, we've sacrificed global orthogonality here. Now let's compare these two properties from FFT to wavelets below. Wavelets, on the other hand, the fast wavelet transform is order n linear time, we'll see fundamentally why later, which is faster than the FFT computational complexity. And two, depending on choice of wavelet, we do get a nice trade-off between time-frequency localization while still maintaining global orthogonality. We'll see why next. I actually took a course in wavelet theory, and I will say if one really is curious to know about the long and detailed process of deriving or inventing or coming up with the wavelet structures from fundamental principles, complete zero, or from scratch, so to say, one should probably actually take a course in the subject because these details are a bit too focused on the question of what exactly is a wavelet, and we lose sight of the big picture of why wavelets. But fundamentally, wavelets are literally just a choice of basis or language to translate to that satisfy a few properties. Wavelets are all orthogonal, which facilitates wavelet transform to new basis or language. Wavelets are also fractals, where one wavelet is made up of dyadically scaled and translated smaller versions of itself. Once again, combined with orthogonality, self-similarity property, enormously it facilitates the speed of the wavelet transform algorithm. Additionally, dyadic scaling and translation allows some time localization and the ability of pinpointing approximately when something happens. So let's think about why the self-similarity property fundamentally allows for fast computation of the fast wavelet transform. Remember, any generalized transformation from one basis to another basis or language can be modeled as a matrix multiplication as shown, which naively done would require n-squared computations. From previous, we showed how the FFT algorithm utilizes some of the symmetry to reduce from n-squared down to n log n. Now, what is the matrix multiplication doing again? Fundamentally, it is taking the signal and taking n inner products with each of the n basis functions. Now remember, wavelets are fractal in nature and are self-similar. What if each basis function was literally just made up of a linear combination of other basis functions, which are just smaller dyadically scaled and translated versions of itself due to fractal self-similarity? Well, due to the linearity of the inner product, we can use previously calculated inner products from the smaller dyadically scaled and translated versions of itself to calculate the bigger basis functions inner products. Or in other words, calculating the inner products for the little guy's wavelets gives you a huge leg up in calculating the inner products for the big guy's wavelets, considering the big guy's wavelets are literally made up of the little guy's wavelets in a linear combination. Or in other words, the big guy's wavelets inner product calculation by linearity of dot product can be broken down into the little guy's inner product calculation and successively and continuously for smaller and smaller scales and so on. That means we keep breaking down into littler and littler guys, and we get to a fundamental building block at the smallest level eventually. This is all illustrated by the mathematical formulation of wavelets by the two-scale relation, scaling function, and multi-resolution analysis properties of wavelets. So a simple recombination of inner product coefficients at the smaller level gives you the inner product coefficients at a larger level, and successively / recursively and so on. At the end of the day, in addition to orthogonality, there is also so much self-similarity between the fractal wavelet basis functions that taking all the inner products intelligently using the previous scale's inner product coefficients by taking advantage of this self-similarity property and the two-scale relation coefficients can be simplified down to from n squared to n, order n linear number of operations. In more detail, once we have the smaller scale dot product coefficients, taking the next bigger scale inner product coefficients is an easier task because we are combining the many small wavelets into fewer larger wavelets. More specifically, there are half as many wavelets at the next larger dyadic scale as there are in the previous smaller dyadic scale, easily seen through the Haar wavelet example shown above and by intelligent engineering design of all wavelets in general. That means the scaling function or two-scale relation coefficients used for calculating the inner products of the bigger guys from the littler guys, so to say, which are on the order of about 2 to 10 coefficients usually depending on the wavelet basis of choice, only needs to be applied half as many times from each dyadic level of scaling up we go. From geometric series, we have n plus n over 2 plus n over 4 plus n over 8 plus n over 16 and so on, and we will eventually finish all computation at 2 times n operations, showing how the fast wavelet transform has so much self-similarity that it can be done in order n linear time, once again assuming n is a nice power of 2. I'm not going to cover the specific details of the fast wavelet transform and the algorithm because that can be easily found in many other sources out there, and there are plenty of readily found algorithmic recipes out there for building a fast wavelet transform. The big picture question is why bother using wavelets and why do they work? The big idea picture for why they work so well and so fast is because of their fractal self-similarity property and also their orthogonality. And the big idea picture for why they are practical in addition to being fast is because they give you some time localization and can tell you approximately when something happened, unlike the global non-windowed fast Fourier transform. One can also see how wavelets are orthogonal by intelligent design. The fundamental smallest building blocks are successively scaled bigger / larger in such a way with the dilations or twin scale equation scaling coefficients such that orthogonality between every wavelet basis vector at every scale is maintained. It's also quite apparent to see visually and by construction if you look at the scaled versions of the wavelets at different scales, they do appear to be orthogonal. The orthogonality property of wavelets can also be very practical for other situations outside of signal processing. And unlike the windowed fast Fourier transform Mollet-Gabor wavelet transform, this can be extremely useful for computational quantum chemistry. Both wavelet basis and the discrete Fourier transform basis are unitary matrix transformations, which are very important in quantum chemistry because this preserves the orthogonality of the basis by just creating a complex valued rotation, so to say, in n-dimensional space, which can be handy when rotating the system to align with the eigenfunctions of the Schrödinger equation. One of the fundamental postulates of quantum chemistry is that all eigenfunctions are orthogonal to each other, which is why the DFT, discrete Fourier transform, not density functional theory, and wavelet basis can be useful as trial test basis functions for optimization procedure in minimizing the energies for the Schrödinger equation in Hartree-Fock computations. For wavelets in particular, there is spatial localization when used as wave functions, which can be quite important in quantum chemistry because we want to know where the atoms in our molecule are probably going to be. Additionally, wavelets scale nicely to higher dimensions by just taking tensor products of the wavelet basis functions in one dimension, which is very useful for image processing or higher dimensional processing, often used in quantum chemistry. Unfortunately, everything in the universe seems to be circular using sines and cosine waves, which are nice looking compared to wavelets. They're smooth and not jaggedy, like the Dobeshi's wavelet, which is ultimately why most of our technologies will continue to use the fast Fourier transform, but the fast wavelet transform does have some interesting niche applications. One of them is information compression, as demonstrated in the diagram, which is really something wavelets are very well made for. So here we have the original function, which takes n numbers of data to uniquely 100% accurately represent. By transforming the original function to the Dobeshi's 4-tap Dob4 wavelet domain, we can represent or approximate the same original function to a pretty high degree of accuracy with just 15% of the n numbers in wavelet domain. That saves us a lot of data and illustrates exactly how Netflix or video streaming services can give you some poor quality image representations with slow internet connection, rather than giving you high quality but incomplete partial images with the limited data transmission capabilities available, just the corner of the screen or something. I mean, this makes sense. Notice how much of the domain of the signal doesn't have much going on, and we can throw away those time/space localized coefficients without creating too much error. This also illustrates how MP3 and JPEG compression works as well. MP3 sound files are on average about 10 times smaller than WAV sound files, and JPEG images are on average about 10 times smaller than PNG images, both without too significant of a noticeable difference. To illustrate data or information compression and the nuance of why translation or change of basis vectors into the wavelets or discrete Fourier transform domain can be useful, if I translate a sentence from English to a different foreign language, the foreign language ends up expressing more or less the exact same idea, but just using different words or using an alternate method. Sometimes, this alternate different method or language used to convey the same idea can be somewhat helpful by expressing the same original idea in a more concise or more intuitive way, illustrating why transforming languages or transforming basis vectors can be helpful. For example, here are some various linguistic examples that I came up with. And notice how by transforming the English sentence to a foreign language, the original idea can be very clearly and concisely expressed using the structure or vector basis of that foreign language, and in a much shorter way, because these examples I came up with don't really have English equivalents, and these concepts only kind of exist in the foreign language, as shown above. The fast wavelet transform and fast Fourier transform, a new alternate language to express data in a way that is possibly more concise or in a way that portrays patterns, similarity, or structure. Intelligent algorithm design taking advantage of fractal self-similarity and symmetries of the bases allows translation procedure to be very quick and efficient, and it is literally just as easy as translating something to Pig Latin, if you know what that is. This is separate from wavelets, but fractals with self-similarity are a very uniquely interesting subject on their own, especially when pondering the notion of Hausdorff measure or non-integer dimensionality. Look at the above examples. You can't really assign one-dimensional measure length to them, yet you can't really assign two-dimensional measure area to them either. They're sort of in between zero-dimensional, one-dimensional, or two-dimensional, with meaning fractional dimensional. This is where the Hausdorff measure is an interesting and useful concept, and plenty of videos about the details of this can be found, but it is worth briefly mentioning because we were talking about fractals for wavelets. So in conclusion, it is difficult to find this unique insight among all the mathematical mumbo-jumbo out there on wavelet theory, which is why this video was created to be at least somewhat accessible to people from all backgrounds. To recap the big picture ideas, we have a sound file or data, which is just a vector list of numbers, and we want to analyze or process the sounds in that data. To analyze this data, we convert to a new basis or language of wavelets or frequencies using these following algorithms. How much computation does the algorithm take? Well, if you use a naive non-orthogonal basis, it's going to take n cubed operations for matrix inversion. If you pick a somewhat intelligently orthogonal basis, naive matrix multiplication takes n squared operations. If we pick not only orthogonal, but a symmetric orthogonal basis, like the fast Fourier transform sines and cosines basis, we have order n log n computation cost. And if we pick something that's even more fractally self-similar, like wavelets, it takes only linear time, order n, which are very quick compared to all the other methods. So, and once again, why are we even bothering to translate to a new basis or language and use the wavelet basis or frequency basis or any basis for that matter? Translating a sentence to a different language or converting your data to a new basis allows for interesting properties and patterns to be found. Though the mechanics are different from FFT and fast wavelet transform, principal component analysis from machine learning uses this exact same fundamental idea. At the end of the day, we can eventually predict or model or compress or interpret the data or information using these methods. So I've been in academia practically my whole life so far, and so interesting perspective I'll provide, signal processing is pretty much never included in standard computer software programming curriculum and is a subject unique to the field of electrical or computer engineering. The focus of the field of electrical computer engineering is not so much to make marketable, user-friendly applications, games, and websites with artistic, aesthetic backgrounds, flashy buttons, and fancy features, but rather to examine and develop the underlying mathematics and physics behind how our technologies function. Though electrical computer engineering will never be as lucrative as the trade skill of pure computer programming will ever be, probably due to today's modern youth's endless demand for gluing their eyes to the screen with distracting mobile apps and games, it is still a beautifully fascinating subject worth having an interest in nonetheless, and hopefully this video illustrated this to some extent. And thank you for watching.